think I'm going to draw in bright green today. Okay. So today we are going to talk about ion formation. Some of you know what ions are already, so you're just going to have to bear with us. And some of you don't. So you are going to have to listen carefully. Okay. So what is an ion? Well, an ion is an atom that has gained or lost one or more of its electrons. So if an atom has lost an electron, what's the consequence for the atom at that point? Now let's do an example here so you can maybe answer that better. So if I were to take, for example, lithium, which looks like this, it's important here to just keep track of what's inside here, inside the nucleus. And we know in its neutral form, lithium's going to look like this. Okay. Now we also realize that this is a full shell. Okay, so we've studied that before. That's a full shell. That's similar to helium's outer shell, right? Helium being a noble gas. And we said that an ion is formed when an atom gains or loses an electron. So if I look at this, and I know this is a metal, can anyone tell me what they think is going to happen with this outer shell electron during a reaction that lithium might have? What do you think? Yeah. Yeah, it'll lose it, right. So without thinking about where it's going to go right now, let's imagine that this electron gets lost. Okay. And what we'll do is we'll redraw what we would have now. Okay. So inside we're still going to have 3 protons, 4 neutrons. Are atomic nuclei ever involved in chemical reactions directly? No. I mean, they play a role obviously by, they have to be there in order to have electrons around. But they themselves don't participate directly in the reactions. Okay, so what we'll be left with is this. Now going back up here, we have 3 positive charges, right? Those are carried by the protons inside the nucleus. And we also have 3 negative charges. And if we were to sum the charges, 3 plus negative 3, we would end up with a nil charge, or a charge of 0. Okay? But now that we've lost an electron, something different happens. We still have 3 positives, but now we only have 2 negatives. Oops. 2 negatives. So if we added them together, 3 plus negative 2, what will we end up with? Plus 1. So what we have here, what we've created, is we've created a positive ion, okay? So we would write that like this. Okay? So this is a lithium ion, and that's the symbol for it, right? It's an atom that has lost or gained 1 or more electrons. So let's do a different example here. Let's look at one that might gain electrons. So from what you know already, do you think that any of the metals will gain electrons in order to react? No, they don't, right? Metals are always going to be losing electrons during reactions, or this type of reaction. So let's look at, why don't we look at oxygen? So oxygen has a symbol that looks like this, 8, 16. So we're to draw its Bohr model. And in a second we're going to switch to Lewis, but just at the beginning here we'll do Bohr models. So we've got that inside the nucleus. We have 2 electrons here, and then we've got 6 electrons up here. Okay. So in order to have a stable shell, oxygen could either go through the process of losing all 6 electrons, but that's not what it's going to do. In a reaction, oxygen will actually import electrons from somewhere else. Okay? And in order to get to that 8 or that full outer shell, it's going to have to import 2 electrons. So if oxygen reacts with something that has electrons to give up, like in our case, right, in our example, that happened to be magnesium, right? But if we look at this, what we'll end up with is something that looks like this still, right? Nucleus remains unaffected. But now, we have this scenario, okay? And, oops, a little bit too far. And so, if we add them up, we've got 8 pluses, and we've got 10 minuses. Okay, if we sum those, we end up with -2. We have 2 more electrons than we have protons. So what we've created is an oxygen ion. The symbol will just be like this. Will oxygen ever form a different kind of ion with some other charge? Do you think it will? Do you think you could ever have an oxygen that's a 6+? No, that's not the way the chemistry works, right? And it turns out, when we start to look at Lewis structures, that it becomes pretty easy to tell what kind of ions these things are going to form. So just hold off for a second, let you guys finish writing out what you need to write out here, and then we'll move on. Okay, so the second part is just going to be determining the ions formed from Lewis diagrams. So instead of constantly having to, draw out all of this stuff every time we want to figure out an ion, it's a much, much easier way to do that, okay? And that starts with just drawing the Lewis diagram. So what we'll do is we'll take a look at the second period, and we'll write out the elements of the second period. So we got lithium, beryllium, boron, carbon, nitrogen. Fluorine and neon. Okay, and we'll kind of split it right on carbon, and we'll say anything to the left of carbon is what type of element? Type of elements here in this second period. Which ones? What are these called? These are all grouped together as one type of element. What type are they? I'll give you a hint. They're shiny. They conduct electricity. Metals, right? Metals. If you look, carbon is an element that is sort of sitting on the staircase of the periodic table. Boron is kind of special. It's technically considered to be a metalloid. I'm not going to, worry about that too much right now. We're safe in this scenario just treating it as a normal metal. These definitely are metals, okay? And then off to the right of carbon are the nonmetals, okay? Now let's start popping in electrons here so that we can see what these Lewis diagrams look like. So it's not quite visible enough. What's that? Okay, so 1 on lithium. Remember, there's two electrons we're not showing right on that inner shell. So we're only showing the outer shell electrons. 2 here, and 3 here. Okay, now before we move on, let's just talk about what sort of ions we're going to form here. So lithium has 1 electron. We know it's a metal. Metals always give up electrons. Lithium has 1 electron to give up. If it gives up 1 electron, what charge is it going to be left with? Giving up an electron means you have less electrons than protons. So it's a plus charge. Are you with me on that? Beryllium gives up 2 electrons. So what charge do you think its ion is going to have? 2 plus. Now for ions, we don't write plus 2. Convention, we write 2, then plus. So what we're saying is there's 2 plus charges here, 2 positive charges, or 2 extra protons and electrons. Okay? Boron, I think you can see where we're going here. 3 plus. Okay? So if we just look at Lewis diagrams, we can very quickly sort out what ions we're going to have. Okay? Now remember, if we look at the first family there, if we look at alkali metals, we've got lithium, sodium, potassium, rubidium, and cesium, and francium. And how many electrons will every single one of those have in its outer shell? They will all have the same, right? The same outer shell electron configuration. They'll all have 1 electron in the outer shell. So when they form ions, what kind of ions will they all have to form? What would be the charge on all of their ions? Yeah, exactly. So it's very quick. You don't have to do a Bohr model. You have to understand why this is true. But if I were to follow down, yeah, that's the ion that's going to form, I'm pretty darn sure. Potassium, yep, same thing. Even these sort of more exotic elements that we don't see very much, we can make a pretty good prediction that even right down to good old francium here, or francium, they're all going to form the exact same ions. So the easiest way is, these are in group 1, they form +1 ions. These are in group 2, they form 2 plus ions. These are in group 3, they form 3 plus ions. You got to be a little careful with that because metalloids have their own sort of thing, but for now we can just go with that sort of convention. Okay, now let's go to the other end of the periodic table and work our way backwards, because something different sort of happens over here. All right? So metals give up electrons, they always form positive ions. These guys, though, they do something different. So let's start with neon first. It's kind of its own thing. It's got a full shell, so it doesn't form ions. It's boring in a way, right? It's not going to be involved in any cool reactions. It just hangs out. Okay? But fluorine, on the other hand, is exciting. You know, you're a science teacher when you like describe inanimate elements as exciting. So if I look, yeah. Okay. Okay. Yeah, no problem. So if I look at fluorine here, right? How many electrons in its outer shell based on the Lewis structure? How many are there? Someone tell me. 7. So if it were to get to full shell city, right? What would I need to do to it? I would need to add 1. Good. And if I did that, right, I'd now have this. Now mimic neon, but I would have 1 extra electron than proton, so I would create this ion. Okay? Stepping farther away, 1, 2, 3, 4, 5, and 6. If I were to add 2 electrons to oxygen now, I get a full shell. And since I've added 2 electrons, and I haven't added any more protons because I can't do that, I would end up with that ion. Okay? And I think you can see where we're going with this. 1, 2, 3, 4, 5 on nitrogen. Need to add 3 electrons in to fill up that shell. Oh, don't put that E there. That E should not be there. Get rid of that little E. Oh dear, why is that so huge? Okay, and we get this. Ooh, we don't. All right, perfect. So there's sort of a mirroring effect here, right? There's a +1 ion group. There's a -1 ion group. There's a +2 ion group. There's a -2 ion group. There's a +3 ion group. And there's a -3 ion group. And then there's carbon, which has 4. So I'd rather just kind of leave it out. Carbon sort of has its own kind of chemistry. In fact, it's got a branch of chemistry called organic chemistry. Carbon does all kinds of neat things. It does not often, I shouldn't really say that, it's not commonly thought of in terms of ionic compounds, but there is such a thing as a carbide ion, which I'm pretty sure that you are adding 4 electrons of carbon to get that. Okay. However, we're gonna kind of not really think about that too much. Okay. So carbon's sort of in the middle, right? It's like pulled in either direction. Does it gain? Does it lose? It doesn't really prefer either, and it sort of it reacts in its kind of in its own way. So as far as what we're doing here, you sort of just leave carbon out a little bit for now. Later on in chemistry, you'll study the chemistry of carbon, and it'll make kind of a lot more sense to you. So this is what ions are. And just one more thing, we'll talk about ions quickly because sometimes there's some misconceptions about what ions do. So the first thing is, ions do not exist on their own in nature. Okay? So it's not like I could ever just be like, hey, look, here's my jar of chloride ions or something. That does not happen. No such thing as a jar of chloride ions hanging around. Impossible. Okay? Where can chloride ions exist? Well, they can exist if they're paired with an oppositely charged ion. Okay? So let's just do one quick example, because the point of this lesson isn't really reactions, it's just to understand what ions are. But let's just do one example of where we might actually see chloride ions. Okay? Where are, for instance, ions, chloride ions in this case? Where are ions? If they can't just hang out on their own, where are they? Where do I find them? One place I might find them is in what's called an ionic compound. And it's just like its name sounds, right? It's a compound made up of oppositely charged ions, okay? And the compound has a net charge of 0. Okay? So one very common ion that's like this is sodium chloride. Now I'm just representing the Lewis structure here with little X's for the electrons. That's just so we can see, you know, where these different electrons come from. So if I expose sodium to chlorine and they react, we'll end up like this. Okay, this gained an electron, so we'll end up with a slightly negative charge, or a -1 charge, I guess. And this will end up with a positive charge. And what do we know about two oppositely charged objects? What do they do when they come near each other? Like if I rub a balloon on my hair and I put it next to the wall, what does it do? It sticks, right? So oppositely charged items stick together. So in the case, you know, in the chemical case, oppositely charged ions literally stick together, and you get this. In real life, what actually is going to happen is you're going to get like sort of like a regular repeating pattern of all these ions, and they'll sort of form like blocks or bricks, and they'll all just kind of like hang out together. Okay? They're like besties. This takes a little while. It's worth it. It's like Christmas colors. All these will have a negative charge, and they'll just kind of like nestle up and balance each other's charges out. And you'll find that you have an equal amount of chloride ions and sodium ions, and you make this thing. Does anyone know? Did I miss one? Oh, I did, didn't I? There. Does anyone know in real life? This, by the way, extends out into 3 dimensions, and it forms, nice regular objects. Does anyone know what we're making here? If we extend this out into 3 dimensions, we imagine that it makes like a very regular repeating structure like this. Can you imagine what that would look like to your eye if it were to grow and grow and grow until you could see it? What do you think it would look like? Would it look like a cube? Probably a little cube. So if I told you that sodium chloride, right, 2 pretty aggressive chemicals, like, I mean, we saw sodium, pure sodium there, we saw a little video of it falling into water and literally bursting into flames. And I'll tell you that chlorine is also highly reactive. It's like the main ingredient in mustard gas, for instance. Very, very bad, dangerous stuff. Okay? However, once you react them in such a way that they have full outer shells, which they would in this scenario, they become actually quite delicious. What would I do with this substance, do you think? What is this stuff? Yeah? You could put it on French fries. It's table salt, right? You are eating sodium chloride when you eat table salt. So what does table salt look like if I look at it really closely? Yeah, it can be fine. Have you ever seen the kind of larger table salt though? Crystals, coarse crystals, exactly, yeah. It forms crystals, and you can see why this might make a crystal. You can imagine, I can't draw it in 3D very well, but you can imagine this is like a box of marbles, okay? Or even better than marbles, actually. A good example is those like little ball magnets. You ever seen these ball magnets before? I think they're called buckyballs. You Google buckyballs. I don't have them arranged like a salt crystal right now, but if you imagine, right, they all sort of stick together, these little silver balls, and they'll pile up on each other, and you can actually form geometric shapes with them. And this is essentially like a large size version of what's going on when we're reacting metal ions with non-metal ions. They form crystals. We're very familiar with crystals. So I'm going to end that here today, because that's enough, and there's some work that goes with this. But before we do that, I'm going to show you some ionic compounds, and you can see that they're all very similar. Some are really neat, they're colorful and fun to look at. So